So we've removed the two acids. The next definitive thing we're told is that there are three esters. Now, if we think about an ester group takes out one carbon and both oxygens, thus leaving behind 3 carbons and 8 hydrogens. So how can we split 3 carbons and 8 hydrogens into 2 groups associated with the ester group? Well, the first thing we can do is we can just say, well, 3 carbons, can become 2 carbons and 1 carbon, so an ethyl and a methyl there. Or we can do a methyl and an ethyl. Next possibility is we have one of the hydrogens there as a formate ester coming from formic acid, and then the other C3H7 is just the 2 isomers of propyl that we've already seen, either the straight propyl or the isopropyl. So there are the four possible esters with the formula C4H8O2. Okay. Now, when we look at these, we see that these two here, the formate esters, have got that hydrogen there, that red hydrogen, and that red hydrogen has a very downfield singlet. It's not going to be as far downfield usually as the acid that we just talked about, but we're going to expect it to be very far downfield. And only spectra H4 now has that downfield singlet now that we've removed the two acids from consideration. So let's see which of these two esters match up nicely to spectrum H4. Now the answer comes from this nice broad peak here, the 6 hydrogen peak here, that's a doublet. Okay, so we want 6 identical hydrogens, and there we are here in the isomer. The pink ones are going to be the 6 identical, split into a doublet because of their proximity next to the blue one. And then this big messy signal here that we would expect to be further downfield because its carbon is directly bonded to the oxygen is for the blue proton. And of course, that's going to be split into ultimately a septet, because you've got 6 adjacent pink hydrogens there, and it's very close together because of course we've had to condense the whole spectrum down because we've got one signal at 1 and one signal at 8, so much harder to see the splittings, but you can start to see there's probably 7 peaks there, certainly a very distinctive multiplet. So we can say that H4 is associated with this ester, and this ester therefore is the missing one that doesn't have a spectra in here because we don't have another proton spectrum that has that aldehyde, or that formate, I should say, proton in there. So now we've got 2 esters left, these 2 here, and if you remember, we created them by saying that we had 3 carbons left that would form the ester groups, and one way you could do that is to have a methyl and an ethyl group. So what we've got here is we've got an ethyl and a methyl group, and an ethyl and a methyl group. Now notice that the ethyl group in both cases are not going to be split further, because here the ethyl group's on a oxygen that has no proton, and here the ethyl group is on an ester carbon that has no proton. And similarly, the methyls are also going to be singlets there, okay, because this methyl is attached to this oxygen, this methyl is attached to the ester. So what we're looking for here are 2 spectra that have a singlet CH3 and an ethyl group there. And remember, the ethyl group is you have a 3 hydrogen triplet and a 2 hydrogen quartet. And the 2 that pop out are H1 and H3. There's the singlet, there's the singlet. So that must be associated with the methyl groups. Okay, and then here is the 2 hydrogen quartet. We know it's a 2 hydrogen because there's 3 hydrogens and 3 hydrogens gone, total of 8 hydrogens, so 2 left, and here's the 3 hydrogen triplet there, and then a 3 hydrogen triplet here, and a 2 hydrogen quartet there. Now the question is, which is which? And the answer is, let's look at the most downfield signals, because you've got ethyl group here, which is bonded to a carbon. Now granted, that carbon's bonded to 2 oxygens, but it's still bonded to a carbon. On the other hand, the ethyl group here is bonded to an oxygen. Okay, so we'd expect this ethyl group to be, or certainly that CH2, to be further downfield than this CH2. Possibly easier to immediately assign that with the methyls. Here this methyl singlet is bonded straight to an oxygen. Here the methyl singlet is bonded to a carbon. So we'd expect this to have a nice downfield singlet, and so that corresponds to the one in H1, and H3 corresponds to the other ones. Okay, so there's the methyl singlet there, close to 4 corresponding to that. Here is that methyl at 2. Okay, now of course we can continue that consideration with the ethyl groups. So here the ethyl protons there, the 3 hydrogen triplet and the 2 hydrogen quartet there. And notice that 2 hydrogen quartet bonded to the carbon of an ester group, and so it's happening about what, 2.3 centered around, so comparable to where we saw the methyl group here that was bonded to the ester group. And now going over to H3, again we got the ethyl group. We have the 3 hydrogen triplet there, the green ones, but then the 2 hydrogen quartet, nice and far downfield. Again, you'd expect it to be further downfield because the carbon is bonded directly to an oxygen. And again, compare how far downfield this CH2 group is in blue compared to the methyl group that has the same type of bonding. Okay, so fairly happy that H1 and H3 correspond to those 2 esters. And when I say fairly happy, I mean really happy.